thanks for the charmful introduction. Well, yeah, my talk is called JavaScript Level 9000 because I had no idea how to name the talk otherwise. And yeah, let's get started. So, as you said, I was previously working for Zynga. I'm doing the benchmarking stuff there, or putting out some open source projects like the Zynga Jukebox back then, which were only crappy HTML5 fixing stuff. But after that, I founded my own project called Level.js, which is something like a JavaScript game engine, but it's not. It's a bit more than a game engine. And Skynet. And Skynet's something like an artificial intelligence that is clustered and stuff like that, so it's something like a hobby for me. And yeah, I was previously also fixing some Linux kernel mod stuff, so I was also implementing like the Radeon driver, or fixing or supporting the older Radeon HD cards back then. And I got into V8 because I thought back then, when being at Zynga, like it's hard to push out a game onto different other platforms if they're not supporting HTML5. So basically, I started to realize that it would be much more awesome when I could just use OpenGL there, or use FreeGlued, or the native GL bindings there. And then I put out a prototype for V8GL, which was basically V8 combined with OpenGL bindings. And I was using it to cross-compile it to other platforms, like on Android or iOS with the Node app stuff. And for even the advantage is that you can even cross-compile it to Xbox 360 or PS4 and stuff like that. Basically, I'm currently focusing on SDL stuff, so my new runtime is based on Node.js and using SDL there, because Node.js is much easier when it comes to networking stuff. And yeah, that's basically what I do. So this talk will be starting low and trying to give you an idea how the data types inside a VM are implemented, and is focusing on the garbage collection concepts, or what the problems in JavaScript are compared to other block scope languages, for example. So it's trying to increase the level straight linearly. So yeah, first, data types. Primitives are the basic understandings of data types, and in JavaScript it's a bit complicated because primitives are also objects, but they are not. And so in these examples, the primitives are like numbers, booleans, null, and undefined. They are the primitive literals, and they are defined as primitives. But for example, strings and regular expressions, because they have a length property and stuff like that, they are objects, but they are handled as primitives. I will explain it later. So the strings are primarily handled in the runtime memory, which means they are deallocated after the call stack is finished, or after the scope was destructed afterwards. And there's a so-called hidden classes idea behind the implementations. So they use like hidden classes to implement everything for you, and the hidden classes are something like the abstraction that you need for your memory allocation stuff. So, and also unique static strings. So if you write down the same string over your code like 10 times or so, then it's only linked as a symbol inside the JIT VM. So yeah, primitives, if you use the native constructor, like calling new number, then you create an object instance. And the object instance is handled differently than the literal of the number itself. So for example, if you type like the epsilon variable here, 1, 2, 3, then it is differently handled in the VM. But of course, it's well, then an instance of object if you use a constructor, or it's not. Arrays and objects are basically all object instances, even the literals. So, for example, array is of course an instance of array, but it's also an instance of object. And the objects themselves are always instances of objects because the literals are defined that way. So the difference here is that the primitives are not referenceable after the scope, or not reusable there, and the object instances are referenceable after the scope is closed, or after the function scope is closed and destructed. So yeah, that's basically the idea of the garbage collector in JavaScript. The hard topics in JavaScript is the dynamic typing stuff. So because previously before the WebGL standard, you had no no possibility to use something like typed arrays. And the idea behind the JIT-VM was then that they wanted to optimize everything as far as possible. So in this example, both have like the same values and the array has the same contents afterwards, but they're optimized in a completely different way. The foo example here is optimized at compile time because the JIT knows, oh, the array has this length and it's closed afterwards, so it's finished at this state. And the bar example is allocating everything dynamically. So at first, it will just, in the first two examples, like the 13 and the 37 values, they will just allocate everything. After that, if you change the type, it will convert everything to doubles. And that's the so-called unboxing, because it has to be unboxed, converted, and then boxed again. Then everything will be converted to doubles. That means the precision of the 13 and 37 values will just be something like .0, and then it's flagged that it's still an integer, or a signed integer in that case. And if you allocate something differently to the values, like a true, which is an object, then it will convert everything to objects or to references, but I will explain it later how that is solved. And yeah, that's basically the difference about the objects and array stuff in JavaScript. What is also important is that objects have unique identifiers, even if they have the identical contents, so that you can use the deep equals comparison, and they will always be like completely different because of the identifier. And but they share the same hidden class behind them. So these examples are identically typed, and they have the identical properties. And the hidden classes inside the VM will use the same hidden class in that case. Hidden classes are based basically on the data types or the values of or the types of the values and the order of the values or the properties. So for example, in this case, the foo and bar example is identical, but the crux example is identical when it comes to the values, but it has the properties ordered in a different way. And if the properties are annotated or assigned to the object in a different order, then it will create automatically a new hidden class. So that is bad, you don't do that. Hidden classes are also an abstraction for functions, because function templates are basically, if they are constructed, creating object instances. So in that case, foo and bar have like, when they are assigned, the same hidden class of point, but it will create a new hidden class for the bar example, because you're assigning a property external to it. So the JIT recognizes it, oh, that's a completely different thing, and I have to create a new hidden class for it. So bar is a fork for foo then. When you want to implement custom primitives in JavaScript, there's the concept behind the value of method and the toString method. So if the value of method is called on binary operators, so for example, if you do something like an addition in that case, it will try to find out if there's an arithmetic value behind it. And if the value of method returns null, then it has no arithmetic value at all, and will be just 0. So in that case, that is the reason why you can add foo and bar in that case, and it will be 0, but you can add another number to it, and it will be the NumE value, because 1, 2, 3 plus 0 is, of course, 1, 2, 3. Value of, as I said, value of is used for the arithmetic value, and if you return a number value instead of null, then it has an arithmetic value, so you can add it to other strings or numbers. And in that case, it will automatically convert it dependent on that. That is, by the way, the same problem with the NAN stuff. So if you have not a number, then when you add not a number to a string, it will give a different result than adding a string to not a number, because it will be the other way around before the conversion. But in that case, it's just like if you want to add a string to it, then you have, of course, like a string conversion from the number. And so the numbers and the values will be identical, except the types there. And after the value of stuff is called, then it will try to determine if there's no arithmetic value, it will try to find out if it's a string or convert it to a string. So that's the reason why you see something like object all the time when you try to dump it into the console or something like that back then. When you are returning inside the value of method, when you are returning an object instance there, then that means that you are a high-level object and not a primitive anymore. That means the toString method is called, and if you add those two examples together, or do an addition to it, then you get the different results because it's just converting everything to a string then. And yeah, that's basically how it works. So now I have to dig into the function stuff and what function templates, function instances, and the prototypes are. So functions in JavaScript, of course, have the prototyping stuff, and prototypes mean that they are something like smart pointers to the memory. And if you have like this example where you construct a new vector there, then the instance of vector will of course be true, but the prototype lookup will the underscore underscore proto underscore underscore array is something like a non-standard stuff to look up the prototype, which is the next up-level hierarchy there. And in this case, it will of course point to vector, then it will point to object because everything is an object instance. And of course, it's not an instance of function. But yeah, the proto lookup will then be null, because if it's null, then the prototype chain is over and the JIT knows, oh no, there's no inheritance at all afterwards. And yeah, that's basically how it works. So if you have something like a new instance from a function, then it will then the direct proto lookup will point to the function.prototype, and that will point to the object prototype, and so on. So yeah, if you want to implement something like entities, because I'm a game engine developer, I have the problem that I want to use vectors and stuff like that. And if I'm implementing a basic entity and I want to reuse the vector methods there, then there's the conceptual problem that you need instances on the prototype in order to have it fully working or integrated with the JavaScript VM. So that means if I'm just pointing the entity prototype, like in this example, to the vector prototype, then I have the same methods, but I don't have an instance of a vector, of course, because the getPrototypeOf method called on the entity instance itself will not point to the vector itself, it will point to the vector.prototype. So yeah, that's basically how the instance of operator works. When you create a new vector instance, like in this example with the "this is correct" mark, then you have, when the prototype of an instance is, or the prototype of a function template is pointing to a new instance, then you have, of course, the correct example with the instance of check there. So yeah, that's basically how function templates are implemented. I hope it was easy to follow. So when it comes to hoisting and closure stuff, it's pretty important to understand hoisting and closures because JavaScript has a problem that the scoping stuff is not easy to backtrace when it comes to memory optimizations. So yeah, let's get started with that topic. Hoisting is using something like hoisting, well, okay, the explanation for hoisting is like you have a variable inside your own function scope, but if it's not accessible or not bound inside this scope, it will just go upwards and try to use the next method out on the outer side. And in that example, I'm binding, I think, yeah, I'm binding foo and bar, but with different names. So it's the other way around. When I'm calling the outer function, I'm using inside the outer function the bar parameter, which is reference to the foo outer scope. So if I'm basically reusing it, I'm binding it. So that is like a closure. But if I'm resetting the foo variable, I'm not overwriting the bar inside the own scope, because that is still referencing not to the original foo, it's just referencing to the state of the foo when the method was called. So that is why foo equals bar will be false then afterwards. Yeah. Closures. So a typical problem is like iterating over an array with objects or stuff like that. And then you have something like you do an asynchronous loader, like loading an image or something like that, and you have an onload method that is called afterwards, and you really want to use DA then, which is the iterator variable there. If you want to use DA there, then of course it will have always the last value, because probably the async loader stuff will be slower than the iteration. And yeah, that's a typical problem like in JavaScript. So a fix for that is just using a closure to hold every variable, so they have the same state when you wanted it to be, and you can just reuse the property at that state there, or the variable at that stage. And yeah, that's basically how closures work. There's something like a function that binds the variables to their own subscope or their own handle scope, and yeah, which they are binding a variable or a property inside their own scope when they would be free otherwise. That's basically what I think closures are. So that leads us to the following problem. We need something like a garbage collector, as we know, because we have object instances and stuff like that, and we want to delete them afterwards, because otherwise our memory will be totally bloated. So the basic knowledge about memory management or garbage collectors are, we have the runtime memory, which are the primitives. So they are cleared directly after your scope has ended. If your scope is being called, and after that the scope is destructed, then all the runtime memory will be just deallocated. And how that works is not important. It's just important that it's deleted afterwards, and you can't be reused afterwards. Regular expressions and strings are somehow exceptions, because they have like the length property and stuff like that, but they are treated as runtime allocations inside the VM. So they're basically primitives, but they're not primitives, but yeah. The heap memory is something like the memory that is available afterwards, but you're not able to use it if you're not referencing it. But yeah, for example, there are function instances, object instances, array instances, and yeah, that's basically what a heap memory is. If the allocations or the references that you're using here are not needed anymore and can be unreferenced, then they are cleared up by the garbage collector. You're creating garbage every time you're something like overwriting the original reference with a new object. So in that example, I have only a named foo object, and I'm creating new garbage when I'm allocating or assigning a new object to it. So that means unreferenced object instances always create garbage. Unreferenced variables or named properties or arguments inside your scope will trigger the garbage collector, so he knows, oh, I have to do something like that. And after each scope that was destructed, the garbage collector checks if the references are still there or if they need to be cleared up. So you can do hints for a garbage collector. A cheap trick is just to set everything to null, because null is not referenceable and it's a primitive. You can set it to 0 as well, but that will be a number, and the optimization stuff is a bit weird there. But yeah, if you do something like you are assigning a variable foo and you have an object instance allocated to it, then you can just dereference it while setting it to null, and then putting on the object instance afterwards. So the garbage collector or the JavaScript code optimizer will know, oh, that's the state where I can clear up everything, and afterwards it's just a plain new object and I need to resort everything. Yeah. So that leads us to the garbage collection implementation itself, or how it works basically inside JVMs. So I'm mostly referencing here to the Java stuff, because Java was one of the first languages that implemented a garbage collector. But most parts of the methods are also used in V8 or the monkey variants from Mozilla. So when it comes to terminology, a garbage is an object in your program that your program cannot reference anymore. So it's not usable at all. A so-called root node is inside the graph, that is inside the garbage collector, is any direct reference your program can access. So that means, for example, local variables on a stack or static class variables, like the length property on an array or something like that. Object instances are live if they are not garbage. That's basically the opposite. Live objects or live object instances are referenced by a root all are referenced by another object instance that is inside the root. You can detect garbage by having basically detecting, like if you have a graph where all the nodes are referencing each other, then you have two different ways to determine if they are still referencing, and one of the algorithms is a depth-first search or a breadth-first search, and both of them will lead you to basically the same result that you know if you're having something like the depth-first search algorithm will just go to each subnode first and then try to determine where there's a back reference, and the breadth-first search algorithm will just go downwards and look at the neighbors if they are referenceable, because you have two-dimensional linking options. Local variables are something like a named pointer that is pointing to somehow anywhere inside the black hole to a memory address. JavaScript has basically only pointers that you can use, so everything inside your high-level language is only a pointer or a number if it's optimized, or basically the primitives. And the hidden classes are the so-called abstraction for that. One method, or basically the method that is used in pretty every garbage collector, is the mark and sweep algorithm. The mark and sweep algorithm has two different phases. The first is the mark phase, and the second is the sweep phase. The mark phase tries to determine everything inside the graph nodes or inside the graph and walks along all the routes that it has, and tries to mark every object that is referenceable from each root node. The program will pause, so your program is like completely stopped, then the mark phase is running and tries to determine all the objects that are referenceable. Afterwards, the sweep phase is going on. The sweep phase is traversing all the marked objects and deallocates them and does all the garbage collection stuff. So it marks everything and marks the memory addresses inside the low-level C++ code or something like that, and tries to allocate them or tries to free up the memory as far as possible. And garbage collection, you have also, in garbage collection languages, you have also the problem that you have fragmentation. So for example, these two examples are identical hidden classes, and they have like two different properties, of course, with the same values, so they're identically. But afterwards, you're deleting one of the properties of one of the instances. So you have something like a fragmentation there. And fragmentation means that memory is free, but memory is free at this specific address inside the memory, and could be used otherwise. So there's the so-called compaction going on that is trying to reorder all the object references that are high-levelly implemented inside JavaScript and repoints them accordingly to new memory addresses. Oh, 3 minutes. In this example, having references to, I'm trying to explain that references are so-called handles inside a JIT compiler. It's basically, in the VM, it's something like a pointer to a pointer. So that means if you're using your bar or your foo inside your code, then it will be just basically a pointer to another pointer. The reason to do so is because pointers can be used as a fixed size. So you have a fixed size memory array, and it's easier to optimize because you don't have to guess what kind of memory size it will use later. The lifetime is determined by the handle scope, and those handle scopes inside a function context are destructed afterwards if the function call is over, and they result in garbage collector trying to clear up everything. So each time a scope is closed, the garbage collector runs over it and tries to determine the references there. Another algorithm to mark and sweep is copying garbage collection. It's something like a base concept where you have like two different static sizes of memory, and you have like the pointers referencing to somewhere in your code. And if you are deleting a reference or creating a new reference, it's just copying it vice versa. So that means from the memory A, it's just using everything that it finds and uses the first allocation in the other memory. Second time it runs, it will just use the first memory and go the same way over and over again. The advantage is that it's super fast and it's easy to implement because you have like 10 lines of code to implement it, but it's of course bad because you have so much to do if n of the references is getting bigger and bigger. A generational garbage collector, like in V8, or I guess in the monkey variants too, is using both of those algorithms and tries to have something like an object lifetime determination. That means it tries to find out if your code can access other objects on previous states in the timeline, and if they are still referenceable or not. If they're not referenceable, that means they have a younger age, because they are just like 1 second old and they can be cleared afterwards. Older objects are the ones that can be accessed anytime. So for example, if you have something like objects on your global scope, you can guess that they are referenceable also 10 seconds afterwards. So that means old objects can be used, can be optimized by the mark and sweep algorithm, and younger objects are basically optimized by the copying garbage collector algorithm. And yeah, 30 seconds, that's the end. And basically that's an introduction how garbage collection works, and I hope you enjoyed it.